Okay, let's get started. I forgot to bring along an attendance sheet for today, which means everybody is present. Okay. Second last class of the semester. Where is the time gone? We're almost there. Okay, so hopefully you are working on your third and final report, which is due Friday night. And on Friday, we will talk about what we expect from you for the final project, which you will be presenting during our exam period the following Friday here in class, 10:30 to 1:15 p.m., and we're all done. Yes?
So we're going to be done by 1:15.
We are going to be done at 1:15. We are not going to be done at 1:14, and we are not going to be done at 1:16.
I just want to make sure we're not going super late.
We are absolutely not going to go super late for the following reason, is that you're going to be doing an oral presentation. You're going to be filming a short YouTube video, and again, I don't know how short, probably between 3 and 5 minutes, with no audio. We're going to stitch all of those videos together into a playlist, which is exactly 2 hours and 45 minutes long. No pause to the playlist. So we will finish it, I promise you, at exactly 1:15. Do you have an exam after that?
No, I have a flight. But
A flight,
no,
okay,
the
all right.
Really late. Like,
Okay.
It's not
Okay.
over like 3 hours.
All right, I promise we will be out of here. We will be done at exactly 1:15, or I will buy you a new flight wherever you're going.
Oh, it's
All right?
too far.
Okay, you can hold me to that. Okay, a point of clarification about the final reports. As I mentioned before, report number one will replace your worst deliverable. If your worst deliverable was 0 out of 5, we will magnify the score of report 1 to cover that. So as you can see, report 2 and report 3 are worth 2%. So if you did perfectly fine on report 1, then your worst deliverable will go from 0 out of 5 to 5 out of 5. If your worst deliverable was 3 out of 5, it'll go from 3 out of 5 to 5 out of 5. Okay, if you sum up your grades in Blackboard, I think it'll sum to something over 100%. We haven't done any of these corrections yet. We will do them when we finish the course. Make sense? All good? Okay. Yes.
What if you do the final project but
What if you do the final project but
don't present it?
then you obtain 0 out of whatever the final project is worth?
11.
11. 0 out of 11. All right? Okay. Let's see. Okay, so again, we're working our way through this this theme on looking inward, where we're really trying to seamlessly stitch together your experience from the human observer's point of view, your experience of the physical world with your experience of a virtual world. In the case of virtual reality, we're trying to swap out your interaction with the physical world and replace it with sensory repercussions that you would expect from the virtual world that you're seeing inside Oculus Rift, right? We're going to finish our lecture on augmented reality today, where we're not trying to replace your interaction with the physical world, but augment or add something to it. And we're going to move on today into lecture 27, looking at technology which is trying to disrupt or otherwise change your experience with the physical world, that feedback loop, but not disrupt it on the outside of your skin, but disrupt it from the inside of your skin. So all interactive technologies that are surgically implanted. Okay, so let's return to augmented reality. We're looking at, like when we did with virtual reality, we started by looking at some of the technical challenges there, right? So thinking very carefully about this action sensory repercussion loop. If we want to project virtual objects into the human observer's view of the physical world, then we need to know exactly where the users are looking, and the best way to do that is to try and get some cameras which are looking at the world in exactly the same way that you are looking at the world. Unfortunately, the best way to do that is to gouge out your eyes and replace them with cameras. Probably that's not going to be a very acceptable solution to a lot of people. So there's lots of tricks with mirrors and optics to try and make sure that cameras can see exactly what the human observer is seeing. And I showed you this little video last time of this virtual creature that was occluded by objects, physical objects that the human observer was looking at, right? So there's some very sophisticated sort of computer graphics work you need to do to get augmented reality right. Obviously, augmented reality is already out there. It depends, the particular augmented reality solution that you're proposing has to do, again, with how intimately, what intimate knowledge you need of that sensor motor feedback loop, right? If all you really care about is the current position of someone, GPS is maybe enough, right? So if you just want to know where someone is standing, like in Harvard Square in Cambridge, and you don't care too much about the actual orientation of their body or their head or their pupils, you can sort of just drop little geotags about what is available nearby Harvard Square, right? So again, there are useful augmented reality apps where you don't need to do anything too sophisticated. But things get interesting when, again, you want to do this very fine-grained painting of virtual information on top of a physical scene. That says markerless artificial or augmented reality. This is left over from an old slide where people were actually trying to put QR codes out in the world. So they were actually trying to mark the physical environment, which would make augmented reality possible. Again, not an acceptable solution, right? We don't want to have our physical environment with QR codes everywhere. So let's assume we're not going to place QR codes everywhere. We're going to operate in a markerless environment. The environment just is what it is. You know, let's say you know the user's current latitude and longitude from GPS on their phone, and you also know where exactly they're pointing their phone. So as long as you're very careful about gyroscope information in the phone, GPS, and you turn on the camera, you know exactly where the user is pointing their phone. And like in the previous example, you can start to paint virtual information directly on top of physical objects in the video stream coming from the phone. So even if you solve the computer graphics part of this, which is putting the virtual components properly on the physical objects, some of these are much easier to infer than others. Let me maximize this slide so you can see it a little bit better. In this cartoon example here, this isn't an actual application yet, but this is kind of where augmented reality companies are trying to go. Which of these virtual components are easier to infer and paint on the screen than others? Or what makes some of these virtual objects harder or easier to paint onto the physical scene?
I mean, any, like the office space, I think that's just a direct label that doesn't have to really depend on the angle.
Exactly, right? So office space, as long as you get GPS and you know more or less the angle that they're holding the phone, you can drop that tag more or less anywhere in the upper left part of the screen. Where did that tag come from, office space? What sensor modality is providing that information? How does the system know that there's office space there? What about apartment for rent there in the top left? Where is that information coming from?
Just like geotags in Google.
Absolutely, right? So Google Maps or wherever else, right? Apartments for sale. As long as there's information that's geotagged, you can put in that's relatively close to the lat and longe of the actual person, that makes sense, right? So there's a lot of mashup technologies going on here, right? So it's not just the sensors on the phone, not just the video stream from the camera, the gyros, and the GPS on the phone, but given that information, what other geotagged information from other data sources like Google Maps or Craigslist are appropriate. What about these other tags in this environment? What data sources are they coming from other than the phone?
I mean, like pothole and 3.1 meters, like that's coming from visual data about the road.
Okay, so the 3.1 meters width of the road and the pothole tag perhaps are coming from the phone, which makes them a little bit trickier than just taking GPS and going and looking for close proximity geotagged items. If you look carefully at this cartoon, you can't actually see the pothole in this hypothetical video stream coming from the phone. Assuming that you did want to do this, and you could imagine some practical applications where someone might be wearing Google glasses and riding their bike or driving their car, and they would like to actually see in their visual stream that there's a pothole coming up. But where's that information coming from in the first place? Or where could it come from? Yes? Other users, okay. So how might other users be providing this information?
Like with ways to like, oh, there's an accident here, and then it's just everyone is driving that way, oh, there's an accident coming up. So if you hit the pothole, you'd be like, hey, there's a pothole here.
Absolutely. Absolutely. So I don't see the pothole, I'm driving my car, I go over it, I feel the bump, I get out my phone and I text or tag something that there's a pothole. But that again, as HCI designers, maybe that's not ideal. Could we do this in a more seamless and automated way?
If the car has a motion sensor and like an internet connection, it should be able to just report that itself, so it detects like a sudden drop.
So we could assume that there are sensors in the car that do that, but thankfully there usually already are sensors in a car that will do that for us. What are those sensors? They're not actually in the car per se, mechanically in the car. They're in the pocket of the person that's driving the car, right? The sensors are already there in the car. So we're thinking about, again, the physical context here. So I have my smartphone, I'm driving my car, and I go over a pothole. What should my smartphone record? You want to develop a pothole detector app for the phone here and report that back to Google Maps to be displayed in a separate augmented reality app.
And like change in the accelerometer, like quick change.
Absolutely, right? So there's a particular acceleration profile that occurs when you're traveling at a certain speed and you go over a pothole. I don't know what exactly that acceleration profile is, but we could take a parking lot and get a bunch of people to drive over potholes with their phones and create a training set and do our normal trick, right? Create our pothole detector. And now we know the pothole, and we make sure to tag the lat and longe using the GPS at the moment we detect that acceleration profile. And if enough people report that acceleration profile at that same latitude and longitude for some extended period of time, add a pothole to Google Maps.
Is this a company in San Francisco that did this?
I don't even remember where I got this from. But I like it because I think it shows off one of the killer apps of augmented reality. A heads-up ad blocker. How would you, let's try that one. So we did the pothole app. What about the heads-up display ad blocker? You're wearing Google Glass and you're walking around an urban environment and you want Google Glass to just paint over any advertisements. How would you distinguish advertisements from non-advertisements in a continuously running visual stream?
A break in the pattern of the building, I guess.
Possibly.
If there's like a website or phone number on it.
Okay, so maybe we do something like the pothole detector, right? The advertising reporting exactly lat, longe, and height and width of advertisers, but that's a little tricky to do. So think again about the political and cultural context around big advertising billboards in an urban environment. If you're an advertiser and you want to do the opposite, which is make sure as many people look at it as possible, what do you do? Make it contrast as much as possible. So whatever tricks an advertiser uses to get you to visually saccade and pay attention to their ads, build that into your app and try and foil it, right?
Wouldn't the ad company just adapt?
Exactly. Now you're thinking like an HCI designer, right? So the moment that there's widespread adoption of Google Glass and the heads-up ad blocker software, what are the advertisers going to do? They're going to push back, and we're back into the advertising arms race, right? Who knows? Perhaps that will happen.
Maybe they'll start
Perhaps not.
advertising on Google Glass.
Ah, yes, exactly. Okay. What other aspects of this cartoon example of augmented reality might be harder or easier to capture and display in a heads-up display like Google Glass or the equivalent? What about beyond this cartoon? If you were assuming you had this hardware technology, what might you try and detect and paint onto someone's visual field?
It'd be really nice if you could look at a bus stop or something and just tell you how long until the bus is going to arrive.
Absolutely, right? So any signage that exists in the real world would be nicer to have virtual signage. So if you're not interested in the bus schedules while you're walking around, you don't necessarily need to see it.
Like, just like basic stats about the world, like, you know, what time it is, what's the temperature like, is there going to be weather change soon?
Okay.
That kind of thing.
Okay. Yep. So real-time weather, time, temperature. Yep. Again, that you might be able to just pull out of a standard website given somebody's lat and longe, right? The interesting ones and the harder ones are the ones that you can't paint on the visual field just by detecting lat and longe.
The location of first responders.
Okay.
So, because I know I've been in the car and not heard the police officer behind me, if I had a visual at that point that I was able to detect that.
Okay.
Feed it to my visual system.
Absolutely, right? So visual responders, again, thinking about physical context here, right? If this is in an urban environment, there is a huge amount of occlusion, right? This is the exact opposite of being out in the prairie in the Midwest where you can see everything, right? A lot of stuff is occluded in your visual field, and there may be certain things that you want to see that aren't actually, you can't possibly see, so you might be able to paint over some of these occlusions. Okay. There are a couple more slides about a particular application we're pursuing in a research project in my lab that uses augmented reality, but we're a little bit behind where I'd like to be at this point in the course, so we're going to skip over slides number, what are we at here? Slides 6, 7, 8, 9, 10, 11, and 12. So on the quiz tonight, material will just be drawn from the first 5 slides of lecture 26. Okay. Obviously, augmented reality, like many of the HCI technologies we're looking at, are just kind of starting to emerge. And the killer apps are going to be from those who are able to cleverly pay attention to the particular kinds of sensor motor loops that people that are engaged in, and how to actually paint that information onto their visual field. Okay, so let's move on now to lecture 27. So now we're going to start to look at interactive technology that is much more intimate in the sense that it's going to interfere in our action sensor repercussion feedback loop under the skin. So let's start again by going back to our standard cartoon here. We have a human actor who is acting on their environment and sensing the repercussions of their actions. But what is really going on inside this box? So let's break ourselves down into 3 pieces. So we have the motor system, our muscles, which are producing the actions. And we have our sensory system, which is capturing some physical phenomenon that is the result of our action and feeds that into our brain. And given what we saw or what we felt or what we heard, we decide on what to do next. So in all the cyborg technology we're going to look at today, the influence is not occurring here, as we saw in the virtual reality system. The interference is here. So in a lot of the technologies we're going to look at now, we are looking at technologies that deal with a breakdown or absence in a part or all of our motor system. So one example of this might be a prosthetic arm. And again, technology that is trying to bypass damaged or absent sensory systems. Okay. We're going to look at some technologies which interfere or mediate between these aspects of the feedback loop closer to the left. And by closer to the left, I mean the central nervous system. Or they're closer to the right, which is the peripheral nervous system. And I'll identify as we go along how close to the CNS or the PNS we're dealing with. Okay. This has been an idea that's been around for as long as computers have been around for, the 1940s. The original idea was proposed as a neural prosthesis. So in the same way that you might have a non-technological prosthesis, like a wooden leg or a wooden arm, a neural prosthesis, as the word implies, is some sort of technological artifact which is going to bypass part of this feedback loop somehow. Okay. Norbert Wiener, you may have heard this name before. He was a cyberneticist. So cybernetics was sort of the ancestor of what we now call AI and machine learning and robotics. The fundamental concept underlying cybernetics was this idea of a feedback loop, which obviously we've spent a lot of time talking about in this course. So way back in the 1940s, when people were starting to imagine this far future technology, they were already thinking about this feedback loop and how to support it, accelerate it, replace it when it breaks down with this newfangled technology called computers. Okay. So here's basically the same picture we have down here. We're assuming that there is some sort of breakdown in our muscles or our sense organs, and we're going to try and bypass that signal somehow. Okay, same picture that you see here. Okay. Again, we might try and bypass just part of one of these systems, or we might try and jump over it altogether and supply signals directly to the input parts of the brain and the output parts of the brain and bypass our motor and sensor organs altogether. That's what's now called brain-computer interaction, so a computer that's interacting directly with the brain. So there really is no clear distinction between cyborg technologies or cybernetic implants and brain-computer interaction. It's really about a continuum about how intimately or how closely to the central decision-making part of the brain that technology is interacting with. Okay, hopefully this will become a little more clear with some examples. So like we've been doing throughout this course, let's start from the outward and work inward. So we're going to look at a technology which is not strictly a cybernetic system because it is not under the skin but on the skin. And it looks like I'm going to have to play this manually. Bear with me a second here. Okay. So this is a harness for people that have suffered a stroke or lost motion in the lower parts of their legs. It's a wearable robot. We're back to a treadmill. Notice the harnesses are also going to help lift the front part of the subject's leg in this case to help them regain the ability to walk. Okay. So we're back to something we've already seen, which is human-robot interaction. So the exoskeleton here is a robot which is actively acting, and the actions of the robot are sensed by the human. The human is doing a little bit of action, but not too much. This particular subject has suffered a spinal injury, so they're recovering the ability to walk. They're acting a very small amount. The robot is detecting their attempts to move, and the robot is acting based on the sensed action. Okay, so in essence, the robot exoskeleton is walking the patient. After a large number of physiotherapy sessions, the subject's body, or muscle and sensor systems are re-experiencing walking. One of the hardest things about recovering the ability to walk is that your spine, and to some degree your brain, has literally lost the memory of what it feels like to walk. So there's a bit of a chicken and the egg problem here. If you can't even remember how to get started, how do you get started? So the idea is for the robot to generate the appropriate sensory stimulation to remind the spine and the brain and the muscles about what it feels like to walk. And when the brain recognizes that, it says, oh yes, I remember this, and starts to supply the right signals back to the appropriate muscle groups. What do you think the robot exoskeleton does as the patient gradually starts to recover the ability to walk?
It provides more resistance against them, or I guess it supports them less and less.
It supports them less and less. So actually it's providing a lot of resistance, right? It's actually holding the patient up, and the exoskeleton is walking the patient's legs. It's the opposite. The resistance or the power of the robot is gradually dropping to zero until it's no longer the exoskeleton walking the human. It's the human walking a passive exoskeleton. This is a process we've seen several times in this class already, which is scaffolding, right? Here it is, the real sensor motor, very tight loop of scaffolding the reacquisition of walking. Right? So basically, the computer system is on this side, right? It has a very intimate relationship with the muscle sensation group, still above the skin. So let's move on now to some actual technology, which is under the skin. Oh, I'm sorry, I want to show you one more example. That was for people that have suffered a spinal injury. There's also a lot of work in, let's see here if I can find it. A lot of work in rehabilitation for stroke patients. And one of the main problems that people that have suffered a stroke is that they developed muscle synergies. And a muscle synergy means that if they choose to move, they cannot move their different muscle groups independently. They're synergetic. So if you want to reach out and grab something in front of you, you can choose to move your bicep or your tricep or your shoulder muscles or your pectoral muscles. In a stroke patient, they do all of it together. So when they try and flex one muscle group, all of the muscle groups flex together. After a stroke, a lot of stroke patients' brains have lost the ability to independently control different muscle groups. So you're going to see that in this particular patient that suffered a stroke. This is a year and a half after a stroke. She's flexing her bicep and also her tricep, pulling her fist towards her, and her shoulder is also rising. So here's an example of this synergy in action. Like in the Lokomat example that you just saw, she also went through a fair amount of physiotherapy where she was wearing an exoskeleton harness, which I think is going to be shown here. Here we go. Same thing here. So now the exoskeleton is sensing all of the muscle groups acting together and is pushing back against her arm and just her arm in this case, and trying to stop some of the muscle groups from flexing. So again, helping her reacquire the ability to flex just individual muscle groups. So basically the robot is helping the patient to break these synergies. Difficult to see in this case here. This is what the physiotherapy actually looks like with this orthosis. You can see the shoulder is not lifting as much as it did before. Okay, after 16 sessions of training. Okay. So still some synergies there. She's being asked to just flex the bicep. You can see there's still some motion in the shoulder and a little bit of flexing of the fist. So 14 months after physiotherapy, still a little bit of movement in the shoulder, but much better than before. Okay. So in order to accomplish this sort of, this kind of therapy, again, the robot exoskeleton has to be paying very careful attention to what the muscles are doing and what the patient is sensing in response. And the robot is trying to move in a way that provides the appropriate sensory repercussions of what they would expect to feel. Okay. Okay. Let's move on to Cyborgs Technologies. There is a very controversial faculty member in the UK, Kevin Warrick, who surgically implanted back in 1998 an RFID tag under the skin. He was able to do this because human subject research laws are much more lax in the UK than they are in the US. If he had done this in the US, he'd probably be behind bars right now. However, he did it and got away with it. We've talked about RFID tags before. They're a pretty simple technology that is passive in the sense that basically the RFID tag is powered off. If you supply it with a little bit of electrical, wirelessly, if you wirelessly provide a little bit of a radio signal, it's enough to power up the system. The system powers up. It does some very simple sensation, sends a signal back out wirelessly and turns back off again. So he recorded a few videos of stunts of him walking through a door, and the door recognized that it was him, and the door unlocked, and all sorts of things. So Professor Warrick wanted to be the first cyborg. There you go. In 2002, he again surgically implanted a device, in this case in the median nerve of his left hand. So now we have a system which is sitting in this particular muscle group in the left part in his left arm here. And when he flexes his left arm, there are strain sensors that are threaded into the muscle groups of the arm that report that it's flexing, and that's picked up by this computer signal. And the computer signal can then send that wirelessly, in this case, to a robot arm. So when he would move his hand, the robot hand would also move. I won't play the video for you in the interest of time, but it looks to me like the robot hand is just kind of moving randomly. I don't think he was picking up a very clear signal. He was just picking up some signal and sending that to the robot hand. But this was admittedly the beginning of what are now 3D printed arms and legs and so on. So far, so good. So the human subject flexes or moves his hand. His own sensor bundles in the muscle group pick up on that signal and send it wirelessly back to the outside world to be picked up by another device. Okay. Is this the first cyborg? Turns out that Kevin Warrick was not the first one to have technology surgically implanted in the skin. Before 1998, there was a lot of initial work with cochlear implants. I don't think anyone here has one. Does anyone know anyone with a cochlear implant? They're becoming increasingly common. So a cochlear implant is very different from a hearing aid, which obviously is wearable. It's not surgically implanted. Assuming that most of the parts of the ear are working but have just degraded somewhat, a hearing aid is sufficient because a hearing aid captures pressure waves from the air and simply amplifies that sound, right? So it's basically just turning up the volume of the incoming sound. But what happens if parts of the inner ear are damaged so you can no longer supply sound or pressure waves to the eardrum and have them be transduced into electrical signals that are sent on to the brain? So now, in a cochlear implant, we are going to try and bypass part of one sensory system, which in this case is the inner ear, and we're going to supply a signal to a device which is upstream. So we're going to talk about upstream and downstream. So upstream means closer to the brain, or the part of your brain that is processing incoming sensory stimulation. Downstream means closer to the actual sensory systems themselves. In this case, the most downstream element of the ear is what? So we have this system that's going to take pressure waves and gradually turn them into something that you experience as sound. And there's a number of stages along this pathway. What is the most downstream part of this system?
Of the ear or the device?
Of the ear itself. So forget the device for a moment, just the ear itself. What's the most downstream piece? The eardrum, right? It's the first place where an actual physical phenomenon, in this case a pressure wave, is captured by a sense organ, right? And then it's processed along this pipeline. We're not going to go too much into the neuroanatomy of the ear, but you all probably remember the snail or the cochlea. So this is this spiral tube in your inner ear that's filled with fluid. And on the inside surface of this spiral tube are these very small hairs. When pressure waves arrive at the eardrum, those pressure waves are passed on to the cochlea, and depending on the frequency of those pressure waves, they vibrate different parts of this spiral, which causes the fluid in the cochlea to slosh around and actually bend some of those hairs. And when those hairs are bent, that triggers an electrical impulse that's passed upstream towards the brain. Okay, so cochlear implants are for those people in which the part of the ear between the eardrum and the cochlea is damaged. How this works is a microphone is placed just on the outside of the skin, and you try and get the microphone very close to where the ear actually is. The microphone picks up sound that is sent to a transmitter, and that transmitter emits a signal wirelessly from the outside of the skull across the skull and is picked up by a receiver which is surgically implanted just on the inside surface of the skull. So now we've got this signal, which is now an electrical signal, and it is passed into an electrode array, a one-dimensional array. So we have a whole bunch of these electrodes, and this one-dimensional electrode array is wound into the spiral of the cochlea. If the microphone picks up a high-frequency sound, then this particular electrode is stimulated. If it picks up a low-frequency sound, this electrode is stimulated. If it's some complex sound signal like speech or music, then we'll differentially excite these different electrodes. When these electrodes are excited, they actually vibrate the cilia or the small hairs inside the cochlea, and the signal gets passed on to the brain.
I read recently about a technology with cochlear implants where they actually use, if that person has even the tiniest bit of hearing in the other ear,
Yep.
because right now it sounds like, like you're underwater and it's hard to differentiate where the sound's coming from.
Correct.
I guess they actually use the way that the brain is translating the sensory information from one ear to, so what kind of interaction would that be? Because it's like going back to the microphone and going to the brain.
Yes, so if you lose hearing in one ear and you only have hearing in one ear, if you do some fancy signal processing, you can take the signal that's being picked up at this ear and combine it with a microphone over here and supply, again, a slightly changed signal. So for those of you that are in this side of the room, you're listening to my voice. My voice is falling on your right ear about less than 1/10 of a second earlier than the same sound is falling on your left ear, because your right ear is closer to my mouth at the moment, right? There's this, it's called the interoral distance, so between ear distance. So you make sense of where a sound source is coming from based on delay. So for those of you that are now directly in front of me, you have basically zero interoral distance from my voice. So they do a lot of signal processing to simulate this delay. And if you do that, then you get the sense that you're hearing a sound in 3 dimensions around you. So 3D surround sound in a movie theater is doing more or less the same kind of trick. Okay, this is very different, however. This is trying to pass over some damaged part of the auditory stream in this case. Did you have a question?
Yeah, well, no, so it's specifically how to do that. It has to be less than 30 milliseconds.
Less than 30 milliseconds.
Yeah.
Okay.
And depending on how large, and so if you're like at 29 milliseconds on one ear versus the other, that will sound like wider, like more, versus the closer you get to the same time, the more like mono it will sound.
Oh, interesting. I didn't know that. Okay, so it's actually quite a complex phenomenon.
Yeah, it's probably, I mean, it depends on the nature of sound, I imagine. And they would probably do it differently for different frequencies.
Okay, so let's focus on some of the technological challenges here, right? So assuming that pressure waves are actually picked up by your ear and transduced through the cochlear into electrical impulses that are supplied to the brain, and you hear a sound, whatever this cochlear implant is doing, the way that it's stimulating these electrodes, the signal that's arriving here, the electrical signal that's being passed on to the brain, is going to be different from this pathway. It's going to be slightly different. So someone who recently receives a cochlear implant, and you speak to them, what do they hear? Anyone have family or friends who have a cochlear implant? No two people's brains are exactly the same, so everybody hears something differently. I had a colleague who had a cochlear implant implanted, and unfortunately in his case, he said it sounded like he was in the front row of a rock concert. Imagine listening to the loudest possible sound you've ever experienced and not being able to shut it off. He could turn off the implant and he would go back to not hearing anything at all. But the particular pattern that was supplied to his brain was interpreting all the other aspects of the sound more or less correctly. He could hear what you were saying or what music was being played, but it was being interpreted by the brain as something that had the volume cranked up to 11, unfortunately. Over time, his brain adapted and was able to gradually tune down the volume. Okay, here's another example. So again, this is tricky to do, but this was based on a lot of verbal reports about what people actually hear with a cochlear implant. Okay, so what you're going to listen to in this video is a simulation of what people hear who receive a cochlear implant, and it depends on how many separate channels you have. So how many electrodes are actually implanted in the cochlea? The more channels, the more independent channels that the implant can stimulate, the richer, more diverse signal you can supply to the brain. Okay, so here's a one-channel cochlear implant. That was speech. Someone was talking. What did that person say? Why did it sound like white noise?
I mean, what white noise is it's like random volume and mid-range signal happening really quickly. initially. So like presumably they only had something in the very middle, but it wasn't picking up any lower high frequency sounds. It was just like
Something collapsed into the middle, right? So a functioning cochlea is providing lots of independent signals, right, coming from the small cilia in the cochlea. Here we've got just one channel which is being turned on and off very rapidly, and for most people that received these early cochlear implants that only had one electrode, unfortunately that's all they could hear. 4 channels? Okay. Anybody understand that? One more time. I don't recommend listening to this video before going to sleep at night. No? Okay.
What kind of bait do you use to catch salmon?
8. No guesses yet? Shall we do it one more time?
What kind of bait do you use to catch salmon?
Something to use to catch something.
What kind of something do you use to catch something, right? So you've got parts of it, right? So again, even without the cochlear implant, your brain is a prediction machine and is trying to match patterns, right? So your brain is trying to do autocorrect here. What are the 2 missing words?
Bait and salmon.
Bait and salmon.
What kind of bait do you use to catch salmon?
Very good.
What kind of bait do you use to catch salmon?
What kind of bait do you use to catch salmon?
Okay. So that's the case. That's basically turning up the resolution on this, right? The cochlear implant, trying to supply a more high resolution signal. It's not the same signal that the intact cochlea provided, but again, the brain is able to interpret it sufficiently to figure out eventually what is being said. Right? Okay, let's carry on. So one approach in cybernetic implants is to try and bypass the damaged sensor modality. Another trick is to capture some incoming physical phenomenon that is meant for one sense organ and supply it instead to a different functioning sense organ. So in this case, this is an application for people that are, in this case, sorry, people that are blind. So in this case, you wear glasses, and inside the glasses is a camera. The camera scans the visual field, so you get basically, you get a pixel array, it's downsampled to grayscale, and now you're going to take that visual signal, the video stream from the camera, and transduce it into an auditory signal and provide it to the ears. So in essence, we're going to try and train unsighted subjects who wear this technology to see with their ears. So again, this isn't actually cyborg technology. There's nothing that's surgically implanted here. Capture something that's meant for the eyes and supply it to the ears. Okay, so how does this work? Again, this was an older technology. It's been improved since then, but the basic idea is we want to try and keep the metaphors that are hidden in a visual signal intact. So if you see something, in the camera, if there's a bright object on the left, then you're going to supply sound in stereo, and whatever sound you supply, the volume on the left is going to be higher than the volume on the right. Brightness is brightness is translated as volume, so big, bright things are louder. Pitch is added to the signal, so higher pitch means the object is higher in your visual field. Lower pitch means the object is lower in your visual field. We've talked a number of times in this course about visual and auditory metaphors. Here we're taking a visual metaphor, things that are higher or lower, and turning them into a auditory metaphor. The pitch is higher or lower. Okay. So if you try and now imagine this, what would this actually sound like? And we'll come back to this question in a moment. Here's an example of one of these soundscapes. So you can see that there are 4 objects here. Some of them are brighter than others, meaning that some are bigger than others. We're going to take each of these 4 objects, and we're going to have a particular repeating sound. So I'm going to play the sound for you. There's an oscillation. And in this video, we're going to remove one of the objects at a time. And when we remove one of the objects, and only the 3 remain, the sound is going to be an aggregate of the 3 sounds associated with those 3 objects. When we place the missing object back and all 4 objects are there, you're going to hear a sound that combines 4 sounds. Then I'm going to remove another object, a different object. You're going to hear a different sound, which is a combination of those 3 objects. Objects that are higher in this visual scene produce a higher pitched sound. Objects which are bigger and are therefore brighter have a bigger contribution to the overall sound stream, and so on. So far, so good? Okay, so the game we're going to play, and we've got 2 minutes left, so this will be the last thing we do today. You're going to close your eyes. You're going to listen to the sound stream, and when you open your eyes again, you're going to tell me which objects were replaced and put back. So with your eyes closed, either the knife is going to disappear and then be put back, or the plate is going to disappear and be put back. So you're going to hear a sound that repeats. The first time you hear it, it's all 4 sounds together. The next time you hear it, it's just 3 sounds in combination. The object is put back. You're going to hear all 4 sounds again. A different object is going to be replaced. You're going to hear a different sound, and so on. 4 objects, 3 objects, 4 objects, 3 objects. I'll play it a couple times. You tell me which object was removed in order. Sound good? Okay, close your eyes. No cheating. Okay, you can open your eyes again. Anybody figure it out yet? One more time. Okay, same video. Close your eyes. Okay. Luckily, if you opened your eyes, it wouldn't have mattered because the video actually didn't play. The auditory did. Let me bring up the video here. Did anyone guess plate and then cup? I think it's plate then cup. I've been playing this video for 11 years. I still am no closer to being able to do it. It seems next to impossible. It's not. People that wear this, their brains are able to learn to interpret what they hear as something they see. Okay, you have a quiz due tonight, and we will talk about the final project on Friday. Thanks very much.